Okay, so now we're going to continue our discussion of alkenes a little bit, talking about what are called cis trans isomers and then the type of reactions that alkenes undergo. So one of the things that makes an alkene very different from an alkane is that the double bond is rigid, so it does not rotate. So what does that mean? Let's actually just draw it out here. So first of all, when I had an alkane, I noted that we could rotate about these single bonds. So for example, I could draw another structure that was rotated about that single bond, and that would look like that. And that these two are exactly equivalent. They're the same thing because compounds can rotate about their single bond. So these would be considered identical structures, okay, just drawn differently. When it comes to double bonds, that double bond is rigid. So this molecule is not the same thing as this molecule because we can't just flip around that double bond. So these are two different isomers, cis trans isomers of this particular alkene, okay? So first of all, I think first thing to get out of the way is what doesn't have any cis trans isomers. If you have two groups that are the same on one of the carbons, so for example, this compound here, this has no cis trans isomers. It is neither cis nor trans because this carbon is bound to two of the same thing. In this case, it's a chlorine. Okay, if we look at our other two examples here, these are cis and trans isomers. So when they're on the same side, they're considered the cis isomer. And by same side, I mean that these two groups are on the same side of that double bond. They're pointed in the same direction. When they're on opposite sides of the double bond, they are trans isomers, right? So one's pointing this way, the other one's pointing that way. Those would be trans isomers. So both of these are 2-butenes, but one of them's the cis isomer of 2-butene, and the other one's the trans isomer of 2-butene. Okay, so the bottom line is if we took a structure, like this, of 1,2-dichloroethene, that actually doesn't specify a unique molecule. That specifies one of two different things because of this cis trans isomers. Are the chlorines on the same side, in which case it would be the cis isomer, or are the chlorines on opposite sides, and thus it's the trans isomer? Right, so again, let's actually color code here. The cis isomer means that they are on the same side of the double bond. So boom, boom, same side. So it's cis. The trans isomer means that they're attached on opposite sides of the double bond. So this is one side, this is the other one. So that's trans. Okay. Again, same sort of idea, right? So cis, they're pointed in the same direction. Trans, they're pointed in opposite directions. Okay, so now we're going to have to incorporate this into our nomenclature, right? And what we're going to do is all we're going to do is name this compound just like we normally would, but either stick cis or trans at the beginning. Okay. So first of all, let's figure out whether this compound is the cis isomer or the trans isomer. So this would be cis because they're pointed on the same side. Those chlorines are pointed on the same side. Now we got to go through and do our nomenclature just like we normally would. We got to find the parent chain. 1, 2, 3, 4. We got to number our parent chain. So our parent chain is a 2-butene, right? And then we have chlorines. We have our substituents. There's one here and one here. Both of those are chloro groups. What do we call it when we have two of the same group? So this would be 2,3-dichloro 2-butene. And now we're going to throw in at the very beginning that designation of cis or trans. So this would be cis 2,3-dichloro-2-butene. Okay. Going to B, again, let's first establish whether it's cis or trans. Here our bromines are pointed on opposite sides, so it's trans. And then from there, everything else is the same in terms of finding the parent chain. So that's those 4 carbons. Numbering the parent chain. I for some reason in this example, numbered right to left. You can convince yourself that you'd get the same answer if you numbered left to right. For these particular examples, either direction numbering would have been the exact same. All right, so again, my parent chain is a 2-butene, and I have a 2,3-dibromo-2-butene, but then this is a trans 2,3-dibromo-2-butene. Okay, and the last one is actually easier than the other ones. Again, we could see that it is a trans isomer. 1, 2, 3, 4 is our parent chain. 1, 2, 3, 4. So this would be trans 2-butene. All right, so that's how we're going to incorporate this cis trans isomer idea into our nomenclature. Okay, so now reactions of alkenes, and specifically they're called addition reactions of alkenes. These are actually something that's commonly used. The hydrogenation of alkenes to create saturated fats is something that occurs in peanut butters and butter and all that good stuff. There are 2 different addition reactions that we're going to talk about here. Okay, one is hydrogenation. This will be adding hydrogens to our alkene. You need a catalyst to do it. It's either platinum or nickel or palladium. You're just going to have memorized that there's going to be a catalyst involved. And what we're going to get at the end of it is an alkane. So you start with an alkene, and as your product, you'll get an alkane. The other type of reaction, it's also an addition reaction, but it's called a hydration reaction because water is being added. You need a strong acid catalyst, which we just represent with the H+. And at the end of the day, what you get is an alcohol. So this is a way to convert an alkene to an alcohol. Okay, let me show you why they're called addition reactions, because I think it will make a lot more sense once we look at an example here. So again, the first step, hydrogenation. This is taking an alkene plus H2 gas. We have our palladium catalyst, and we're going to get an alkane at the end. And notice exactly what's happening in this reaction here. Basically, what's going down is we are breaking one of the bonds of our alkene double bond, and we're adding on those hydrogens, right? That's what's happening in this reaction. So we start out with an alkene. The hydrogens that were in hydrogen gas are now being placed on either side, and we've gotten rid of one of our 2 covalent bonds. Okay, so that's why it's called an addition reaction, because you're adding atoms to either side of the double bond. Each carbon on either side of the double bond is getting a new atom added to it. In case of hydrogenation, they're both hydrogens that are going to be added. All right, so let's do the hydrogenation of 1-butene. So first we got to be able to draw 1-butene. How many carbons should I have? There's my 4-carbon parent chain, and now I need to make sure that my double bond is in the correct position. It should be, since it's 1-butene, that means it's between carbons 1 and 2. And then I'm going to add H2, And this is going to be in the presence of a catalyst. You can pick any one of those three, really just pick one and stick with it. I mean, let's do platinum. Okay, and what am I going to get out of it? Notice that I'm not adding or subtracting any carbons, right? So I should still have my 4 carbons at the end. And actually, you know what I'm going to do is, okay, and what I've done is I've added a hydrogen here and a hydrogen there, right? So here's carbon 1 and 2, carbon 1 and 2. I've broken the double bond between carbon 1 and 2, and I've added a hydrogen to each one of those carbons. Now, in our bond line structure, we usually don't draw the hydrogens. Those are kind of implicit in the drawing. So actually, I could just draw that like my equation like this. I explicitly kind of drew them in there and colored them blue so you guys could see what's going on. But it would be perfectly fine to not have them in there at all. All right, and so this is just a way of converting. You can see here now it's done in the expanded form, or not the expanded form, I'm sorry, your condensed structural formula. And notice how this carbon used to have 2 hydrogens on it. Afterwards, it will have 3. Likewise, on the other side of my double bond, there was just 1 hydrogen at first, and now it has 2. Okay, so those are where those hydrogens that were originally in the H2 gas have ended up. Okay, and again, this is a way that they've convert unsaturated fats into saturated fats in the process of creating, I guess not butter, because butter's natural, but margarine, the peanut butters, the vegetable cooking shortening, et cetera, et cetera. Okay, so here, what am I going to do? Again, just sort of predicting products. I will get rid of this double bond here. And that means a new hydrogen has to be added here and here. So this would be CH3. Now it's CH2 with the single bond, CH2 with the single bond, CH3. All right, so again, the big change is occurring with the number of hydrogens that were on each one of these carbons, as well as the breaking of that double bond. If I'm going to do it all strictly in bond line structure, right, all I'm really doing is getting rid of and replacing with hydrogens, and I don't even have to explicitly draw those hydrogens in there. So it's as simple as just not drawing that extra double bond, or that extra line which represented the double bond. Okay, so now hydration reactions. We're adding water to this and we're getting an alcohol at the end. So let's first just notice that this is very similar to before, except for now I have my OH group from water that's going to be added to one of these carbons, right? So that's this carbon here is getting the OH group added onto it. And my other hydrogen is being added to the other carbon. So that's that carbon there. Okay, these are a hydration reaction. We say that because water is being added on in an addition reaction. And again, these are going to be catalyzed by acid. Okay, so we just represent that as H+. Notice that we're putting our catalysts on top of the arrows. That's a typical way to represent that there's a catalyst involved in this reaction. Now there is another kind of trickier aspect of this than with the hydrogenation reactions, and that is, where does that OH group go? Right, I put it on carbon 2. So I put it on carbon 2 instead of carbon 1. Why would that be? So that's the rule of these hydration reactions, is that the OH group adds to the more highly substituted carbon. So by that I mean the carbon that has the most carbons bound to it. So carbon 2 is bound to 2 other carbons, whereas carbon 1 is only bound to 1 other carbon. So carbon 2 is what gets the OH group. Likewise, the flip side of that, I guess I messed up my color coding here, but whatever. The flip side of that is that the hydrogen from the water attaches to the carbon that has the greater number of hydrogens. So it's kind of saying the exact opposite. Carbon 1 had 2 hydrogens on it over here. Whereas carbon 2 had only 1 hydrogen bound to it. So the hydrogen is going to be added to the carbon with the more hydrogens. Those are just inverse ways of saying the same thing. I actually think of it more as what I've underlined in blue here. I'm going to put the OH group on the more highly substituted carbon. And again, more substituted means more carbon, more carbon-carbon bonds. Okay. So let's do this example here. We're going to do the hydration. So first of all, I'm going to identify where my double bond is. I'm not even going to pay attention to the other part of the molecule because this is where the action's happening, are those 2 carbons. So even without doing anything else, I can go in and write this back half here because I know that that's going to be the same. The difference is now going to be, again, that this bond gets broken. This one of those covalent bonds in my double bond gets broken, and I replace that with the OH on the more highly substituted and the hydrogen on the less highly substituted. Okay, so in terms of kind of getting a correct balanced chemical equation here, this CH, now it's just going to have a single bond and the OH is going to be on that carbon, whereas this is going to turn into a CH3. Okay, now let's look at this next example. Notice that here now, as opposed to before, we had the double bond on like the end of the molecule. Here it's on the inside. So both of these carbons have 2 neighbors. So this one has 2 neighbors. Yeah, I mean, actually, let's do this. My orange carbon has 2 neighbors and my blue carbon has 2 neighbors. So neither one of them are like more highly substituted than the other. In this case, you'll actually get a mixture of 2 different products. So we'll get a mixture where one of my products, the OH group has joined onto the blue carbon. And on my other product, the OH group has joined on to that orange carbon, right? Since both of them have the same number of carbon neighbors, same number of carbon-carbon bonds, neither of them are preferred, so we'll get a mixture of both.